Hello and welcome to the Unit 4 Chapter 10 Notes on Gases. This is meant to be a review of the the gas law information that you learned in first year chem. We're looking at units for the parameters that we measure for gases, we're looking at the laws, and then kinetic molecular theory. So characteristics of gases, again, we're going to treat them separately in our discussions from the other states of matter, solids and liquids, because gases are able to expand to fill their containers. They are highly compressible and they have extremely low densities. And so we're going to take a look at kinetic molecular theory, which helps us to describe what the gas particles are doing and how they're behaving, which then will help us to better explain these characteristics that make gases unique from liquids and solids, and it will also help us to explain the gas laws that we're going to go over. So kinetic molecular theory is stating that gases behave in a certain way. So it says that gases consist in large numbers of molecules and they're in continuous random motion. So we see this little picture over here. You looked at the simulation where we saw that the particles in the gas are moving in straight lines until they run into something. So the reason that they expand to fill their containers is because they're not inhibited by neighboring molecules. They just keep going in a straight line until they bump into something. So if the container wall gets pushed out, then that means they're going to keep traveling and fill up that space until they hit it. If the container gets smaller, well, again, there's, the gas particles just keep going until they hit that container wall. And obviously, if there's a bunch of empty space between the particles, then, there's room for them to be confined into a smaller space. Speaking of volume, the combined volume, so the second point here, combined volume of all the molecules in the gas is negligible relative to the total volume in the gas. So we will eventually adjust for the reality of real particles and that every gas, doesn't exactly behave ideally. There are some, especially in larger gas molecules, that the size does start to become a factor in gas behavior, but in general, there's so much empty space between the particles of a gas that the teeny tininess of the particles themselves can be kind of thought of as negligible in comparison. And then lastly, attractive and repulsive forces between gas molecules are negligible. So when we talk about liquids and solids, there's going to be a discussion about those attractive forces. That's what hold them together in those states of matter. But when we have a high enough temperature for a particular substance to have it be in the gas form, the gas molecules are no longer inhibited by attractions to one another, and so they just kind of move around the container independently. And we assume that with all the empty space and all the energy the gas particles have, that if they do happen to run into each other, they're not going to be sticking together because they're moving too fast to do so. So those are some of the pieces of kinetic molecular theory. One of the other things that's not listed here is the relationship between average kinetic energy and particle speed. And so we also should note that gas molecules at a certain Kelvin temperature, a certain absolute temperature, are all going to have the same average kinetic energy. And then we'll talk about the relationship with velocity in a second. So again, there's a connection also between the average kinetic energy of gas molecules and their temperature. And so any gas at a given absolute temperature is going to have the same average kinetic energy. Notice like the average kinetic energy. So when you think about what we talked about, or what we saw in the simulation looking at the Maxwell-Boltzmann distributions, we saw that fact here. So we know that there's a relationship between kinetic energy and molecular speed. The kinetic energy equation is 1/2 mv squared, m being mass, v being velocity, and we should have seen in the simulation that as we heated up the container of molecules, that, well, first of all the particles were not moving the same speed. So that's what this graph is depicting, that some of the particles are moving faster, some are moving slower, and though there's a most probable speed, so that's going to be where the peak is the highest, there's quite a distribution overall, but there's an average. So just like we said, there's an average kinetic energy for a given temperature. There's, if we averaged all these speeds for all these molecules, that's the connection we can make. Now, we should have also noticed when we increased the temperature of the particles, we saw the curve shift to the right. So increasing temperature increases kinetic energy and therefore increases the velocity of the particles. And you should have also noticed that the curve not only shifts to the right, so the peak is shifted to the right when we increase temperature, but it also flattens out a little bit. So the lower the temperature is, the more the peak is going to get higher and shifted to the left, meaning there's less variety of speeds. And as we increase the temperature, the peak flattens out and shifts to the right. So there's going to be a greater distribution of a more variety of the speeds that the particles are traveling. All right, so some other things, and then we'll come back to this another day, but you've got a couple different things to look at here when we're looking at the particle speed. So again, in the simulation, we should have observed all the particles are not going the same speed, but there's a most probable speed. So that's like, the most molecules, the largest fraction are going this particular speed that, that's what's represented by the peak of the curve. If I added up all the velocities and found the average, that would land us right here. And then if I actually tried to connect, so we said that at a given temperature, all the particles, the average kinetic energy is the same, no matter which type of gas, as long as you're at that same temperature. So the URMS, that's the root mean square speed, that is like if I took a particle that had that average kinetic energy as its kinetic energy and found the velocity that corresponds to that, that would be where this lands me. So obviously, when we were looking at the shifts in the graph, when we heated up the molecules, we saw that all these, the peak and everything moved to the right, and of course it flattened out a little bit, but they would stay in the same positioning. So the root mean square, the velocity that corresponds to the particle that actually has the average kinetic energy, that is going to be just to the right of the peak there. All right, so we'll come back to this another day when we talk about some other things, but just to give us an idea about what that was that we saw in the simulation. Okay, so some other characteristics. Pressure. From physics, we should know that pressure is the force applied to an area, so force divided by area. So for, like atmospheric pressure, we're looking at the, the weight of the air pressing down. So although, generally we think of a gas confined in a container, we don't think of gravity as affecting it, but we've got such a huge body of gas molecules like we do in the atmosphere. At some point there is, gravitational effect that kind of holds some of the gas molecules in closer. And then those particles, when they hit the surface of the Earth, exerts a pressure. So that's what atmospheric pressure is. And we will typically refer to standard pressure as the standard or normal atmospheric pressure at sea level, and that's defined as 1 atmosphere. So ATM is that pressure unit for, corresponding to standard pressure. So ATM stands for atmosphere. There's also, that's equivalent, when you look at the unit equivalences, that's 760 torr, and a torr is the same thing as a millimeters of mercury, or we've got, that's equivalent to 101.325 kilopascals. So for gases, when they exert pressure in a container, they exert pressure by hitting the container walls. So that's another thing that we should keep in mind that we know from kinetic molecular theory. Some units here, so millimeters of mercury or torr, you can see this setup of a barometer. We've got the pressure of the air pressing on the surface of the mercury, and then there's an evacuated tube here, and essentially however high in the tube the mercury goes, is pressed, that height is this millimeter of mercury measurement. So when we look at, well, where do you get that weird unit, millimeters of mercury? That's it. It's literally a length measurement that corresponds to how hard the atmosphere is pushing on the surface of the mercury. So there's all the other units. So again, an atmosphere we said is 760 torr. A torr is the same thing as millimeters of mercury. So so here's all the equivalencies. You will be given a couple of these on your equation sheet. Any others that you need to convert between, you'll be given them, although, you should be able to get from pascals to kilopascals. Pascal is the SI base unit. So like if you look at, what force, a Newton is a force unit divided by an area in terms of SI base units would be meters squared. So that's where Pascal comes from. You kind of don't need to know that for everyday functioning here, but just, because of Pascal, it's such a gigantic number. 1 Newton over 1 meter squared, like that's a huge amount of force over, that's a huge amount of area for the force to be applied. So, typically we'll work with things in kilopascals, or atmospheres. PSI is pounds per square inch. So again, I would just have these in your notes and know where to get to them if you need to convert between pressure units, and recognize them all as pressure units when you see them. Another thing we should, sometimes there's random questions regarding manometers that come up. So this is, obviously usually we use pressure gauges and pressure sensors, but this is kind of an old school apparatus that, conceptually I think is good to look at, where if we, have a gas that's trapped in a container and it's open to the atmosphere, the difference in the heights of the mercury in this U tube is going to be the pressure difference. So obviously if the it's like on the opposite of a tug of war, it's a push of war. So if the atmosphere pushes more and pushes the mercury closer up higher on this side, that would mean that the atmospheric pressure is higher than the gas pressure. If it's the opposite, like in this picture here, it would mean the this gas has a higher pressure than atmospheric pressure. It's kind of winning the push of war. So that's why they're giving me this formula, that the pressure of the gas must be atmospheric pressure plus whatever that height difference is. And this, although, we don't use manometers really anymore in class or anything, this is actually a good concept to understand when we do our lab involving the molar mass of a gas, because we're going to use we have the liquid level inside and outside a container equal. If I have a gas inside the container and the liquid level, the water level, much like this here, like the mercury, if the water level is equal inside and outside, that actually tells me that the pressure inside the container is equal to that outside the container. And that is pretty useful, because then without a pressure meter to measure the gas itself, if I know atmospheric pressure, I can figure out the pressure of the gas. So that's pretty cool and something that we use in our lab. Okay, so the laws. Let's just review these quickly because you went through them in the simulation. So Boyle's law, again, when we're talking about these individual, Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law, we're keeping the other two variables constant. So pressure, temperature, moles, and volume are the four variables we talk about for gases. We're keeping two constant and changing two. So that's when we talk about these laws, that's what we're referring to. So pressure and volume are inversely proportional according to Boyle's law. So if I squish a gas into a smaller volume, the pressure is going to increase. And again, that should kind of make sense. Well, we saw these graphs also in the simulation. And there's the equation for it. But it should make sense in that, again, pressures are exerted by gases hitting the container walls. And so if I expand the size of the container, the gas doesn't have to travel the gas travels further before it hits the container wall, and it's going to hit the container walls less frequently, and therefore result in a lower pressure. So the things that we see in these relationships, these numerical relationships from the laws, we should kind of be able to explain with kinetic molecular theory. Charles' law is the fixed amount of particles of a gas in a volume, and when we change temperature, again, pressure is constant. So this is only going to be the case if you have like a piston scenario, or if you've got a balloon where the volume can change. And a lot of times in our experiments and stuff, we're not going to have a variable volume. So, but in those cases where volume is variable, their volume and temperature are directly proportional. So we'll see, that straight line plot. So, this is especially useful if we're working with gases where we've got reference information at atmospheric temperature, not atmospheric temperature, standard temperature, 273 Kelvin, and we need to figure out something at the temperature we're actually working at. So that's what Charles' law is useful for if I want to figure out, a density or something, if I'm at a different temperature than the standard that's reported in the book. Gay-Lussac's law, so that's temperature and pressure, so those are directly proportional, much like Charles' law, the temperature and pressure and volume and temperature are all, those are all directly proportional, meaning when one goes up, the other goes up, or when one goes down, the other goes down. And again, if temperature is related to particles, their kinetic energy, then if I increase temperature, they're moving faster. If they move faster, they're going to hit the container walls more frequently and exert a greater pressure, and vice versa. Avogadro's law. So this is, it should make a lot of sense in that if I have more moles of a gas, they're going to take up more space, and that's assuming that I'm at the same temperature and pressure. So especially when we get into stoichiometry problems, which we'll get into, we can use this to our advantage. If I look at coefficients, I'm talking about the reaction happening at standard conditions or at whatever assigned conditions. If I have 2 moles, combining and making 1 mole of something, well, that's going to take up half the volume. And volumes are very easily measurable, and again, we can use that to our advantage and to tell us quickly about the number of moles without actually using the ideal gas law equation. So that is Avogadro's law, so moles and volume are directly proportional. And so then if we combine, so here's all the relationships we have. So the only pair of variables that are inversely proportional are the volume and pressure from the 4 laws we've looked at. So volume and temperature, pressure and temperature, volume and moles, those are all directly proportional. So these are, again, if I have a need to change conditions, which in particular, when that would happen is if I have, I have reference values recorded at standard conditions, and then I want to work in atmospheric conditions or current conditions. These equations are useful for that type of scenario, where I've got 2 variables and I need to adjust to new pressure, new temperature, new volume, whatever. Combining these concepts all into one equation, we get this relationship. So that's maintaining the directly proportional between, between the V and the P and the V and the T. The V and the T and the V and the N, and maintaining the inversely proportional between the P and the V. And we wrap that into an equation, and that gives us the ideal gas law equation. So if you look back on the previous slides, there were a little K constant that was specific to each scenario of how many moles were there and how many, what the pressure was or temperature was. So when we combine all these values into the same equation, though, there's a constant that is truly constant, like the same, no matter which gas we're talking about. So this gives us this equation, P times V equals nRT, and R is called the ideal gas constant. You may also see it referred to as the universal gas constant. And essentially, it's a constant value. So it's going to be given to us for whatever it's given to us on an equation sheet. And the only differences between these values is that they've just got different units. So the key when we're doing ideal gas law equations is whatever the units are on the R value that we're using, we want to make sure that whatever we plug into the ideal gas law equation, all the other variables have the same units. So you can pick a gas law constant that is appropriate for the units you already have, or you can take the units for pressure, temperature, whatever, and convert them to whatever the R value is, depending on what's more convenient. But again, these values will be given to you. In particular, I believe you'll be given the first one and the second one on your AP equation sheet. So we'll be getting into what to do with this stuff in the future. But again, that's just in a nutshell the laws that we should already be familiar with, and again, the stuff that you saw in the simulation. Oh, the other thing real quick, in the simulation, this is a slightly different simulation than the one that you were working with, but just so we can see the 2 different types of moles in here. So notice we've got a volume, I'll lock that, the pressure, the temperature, and so we've got a pressure of 1.82. If I put in an equal amount of gas B, notice that my pressure, if it's double the molecules, then I get double the pressure. So temperature is the same, volume is the same. So the only thing I've changed is double the number of particles. Now, if I clear this all out, I'll do that. Let them out. And just put in, did it again, put in 2 of the same thing. Hold on. Just put in gas A. Put in gas B. So notice the pressure, again, it's around what it was before the first time when it was just gas A in there. It doesn't matter what the gas is, what the identity is, what the pressure is, because if you look at that equation, the N, it just needs number of particles. So similarly, if I have gas B if I have put another pump of gas B, so notice 2 pumps of gas B, so whatever, twice the moles that were there before, that gives me the same pressure as having 1 pump of gas B and 1 pump of gas A. It will also give me the same pressure if I have in, oh, now I managed to put in both again. If I put in 2 pumps of just gas A, there we go. There's 1 pump, there's 2 pumps. So notice I'm getting exactly the same pressure every time. So that is what Dalton's law of partial pressures has to do with. It really is, heavily connected to just understanding the gas law equation, and that, at a certain temperature, in a certain volume, a certain number of moles gives me a certain pressure. If I double the number of moles of gas, it doesn't matter what kind of moles of gas it is, just if I double the number of particles, I double the pressure. Or if I increase it in some way, I'm going to increase the pressure. And that's what Dalton's law of partial pressures is if I know information about each little part, or each of the, if I know some information about one gas, and then I know the total pressure, I can use that to figure out the information about the other gas. Very, very useful, and something that we'll be using in our future problems.